Hello dear, welcome back to the world of chemistry. Today we will discuss the preparation of alkyl halides, that is preparation of alkyl halides. One of the most important method to prepare the alkyl halides is from the alkenes. In this process, what we can do, we take alkenes and we treat these alkenes with the halogen acids. When we treat them with the halogen acids, we get the alkyl halides. Okay, see here, I will write here that alkenes. Okay, we will prepare alkyl halides from alkenes. If I will write here that we have any alkene and we treat this alkene with halogen acid, and it gives us alkyl halide. Okay, dear. Now see one example. We have CH2 double bond CH2. This is an alkene known as ethene. I treat it with halogen acid HCl and it will give us CH3, CH2 and Cl. This is an alkyl halide. Okay, now this is ethene, this hydrochloric acid, and we get alkyl halide. The name of this alkyl halide is chloroethane. Okay, now in this reaction we use different halogen acids and different types of alkenes. Now we will proceed this preparation and we will see some of the questions which were asked in this topic. Okay, now see here, my dear, we have the halogen acids as HF, HCl, HBr and HI. Okay, first of all we have one question in this, that is, what is the reactivity of halogen acids with the alkenes? If we keep any particular alkene, say I am taking ethene and I am reacting these halogen acids with that ethene, what will be the reactivity of these halogen acids? Okay, now if I see the reactivity order of these halogen acids, the reactivity order of these halogen acids is as HI is more reactive than HBr, and HBr is more reactive than HCl, and HCl is more reactive than HF. Why this is happening? Why HI is more reactive than HBr and HBr is more reactive than HCl and HCl is more reactive than HF? We know that the dissociation energy for HI is less because the bond length of HI is more, hence it dissociates easily. Okay, and the bond length of HF is short. Okay, and this has a more dissociation energy, that's why its reactivity is least. Okay, now if I take the alkenes, I have two types of alkenes. One alkene will be symmetrical alkene, and other will be unsymmetrical alkene. I will react these halogen acids with the symmetrical alkene as well as with the unsymmetrical alkenes. Okay, now first of all we will see the reaction of these halogen acids with the symmetrical alkene. Okay, now see here, I will take a symmetrical alkene. Let's take an example of CH2 double bond CH2. This is a symmetrical alkene. What is symmetrical alkene? If we see this double bond, if we have the same groups on either side of this double bond, in the right side of the double bond there is a CH2, and in the left side of the double bond there is a CH2, and this alkene is a symmetrical alkene. Okay, if we add HCl to this symmetrical alkene, I will get CH3, CH2 and Cl. Okay, as I have told you that this alkene is ethene, this is hydrochloric acid, and we get chloroethane. The first question in this reaction is which type of mechanism this reaction follows. Okay, see here is a double bond. That double bond means there is an electron density. Okay, there is a electron density, and if there is a electron density, there are loosely bound electrons, and this HCl, when we take this HCl, it dissociates as H plus and Cl minus. It dissociates as H plus and Cl minus, and we have electron density here, and we have electrophile here. This H positive is an electrophile. That means this electron loving species, and this H positive will attack either this carbon or this carbon. There's an equal probability. Okay, if I will attack this hydrogen will attack on this carbon, it will form CH3, and there will be a single bond, and this bond will break down. Okay, when this H positive will attack on this carbon, this double bond will break down and it will form a bond with the hydrogen, and we get CH3, and the carbocation is generated here. Okay, when this carbocation gets generated, then Cl negative will attack on this carbon. And we get that product, that is CH3, CH2 and Cl. Okay, now this first step is a slow step, and this is the fast step. Okay, in the slow step, the electrophile attacks on the substrate, and in the second step, the nucleophile, that is Cl negative, attacks on this carbon. But in the slow step, the electrophile attacks. So this is the addition reaction. This is the addition reaction actually, because the substrate HCl gets added to the substrate, H on this carbon and Cl in this carbon. Okay, this is an addition reaction. But what type of addition reaction it is? In the slow step, the electrophile has attacked on the substrate, then we can say this is an electrophilic addition reaction. This is electrophilic. It's an electrophilic addition reaction. Okay, it's the electrophilic addition reaction. Okay, in case of symmetrical alkenes, we don't have any problem whether this H attacks on this carbon or this H attacks on this carbon. If this H attacks on this carbon, it gives us 1 chloroethane, and if this H attacks on that carbon, it also gives 1 chloroethane. There is a single product formation. Okay, now the case is here. If we take unsymmetrical alkene, CH3, CH double bond CH2, and I will treat it with HBr. Okay, now what will happen? The addition of HBr will take place on this alkene. If I will see, I will get two products here. One will be CH3, CH2, Cl, and other product will be CH3, CH, Cl, and CH3. Okay. This product is 1 chloropropane, and this is 2 chloropropane. Sir, can you explain us, my dear students? You will ask that, sir, if two products are formed, can you explain how these two products are formed? Okay, how 1-chloropropane is formed and how 2-chloropropane is formed. These are two different products. That is, if we take unsymmetrical alkene, we get two separate products, two different products. Okay, and I am saying that this will be a minor product, this will be a minor product, and this will be a major product. And we have to explain why this compound is a minor and why this compound is a major. Okay, now we will explain it on the basis of the intermediate which will get formed during this reaction. Okay dear, now keep this thing in mind so that we can do a mechanism of this reaction and we can explain why these two different products will be formed. Okay, have you seen it? Okay, now see how it is formed. See how it's formed. See here, my dear, it is CH3 CH double bond CH2. You know, in the first step, when I take HBr, when I will treat it with HBr, and this HBr will dissociate as H plus and Br minus. Okay, in the first step, this H will attack on this substrate. Okay, this H can attack on this first carbon or this H can attack on this second carbon. Okay, now see here, if I will take this as a carbon number 1, carbon number 2 and carbon number 3. Okay, in the first step I am taking that CH3 CH2 single bond CH2. What I am doing, this H has attacked the carbon number 2. When it attacks on the carbon number 2, this bond will break down, okay, this pi bond, and the hydrogen will get attached to this second carbon. Okay, and we get CH2 here. When this bond will break down, the positive charge will get created here. Okay, this is the positive charge. Okay, now if this H will attack on the first one carbon, this first carbon, if this H will attack on the first carbon, what will be the intermediate? The intermediate will be like that, CH3 CH and CH3. Okay, because here we have CH2. When this will attack on the CH2, it will become CH3, and this bond will go in this side. Okay, and CH3 and the positive charge will get created here. So in this process we get two carbocations. These are the reaction intermediates, and these reaction intermediates are called carbocations. As we have already discussed, what are the carbocations? It is the species where the carbon have a positive charge and 6 bonded electrons. Okay, now see here, this is a primary carbocation. Okay, and this is a secondary carbocation, and we know that secondary carbocation is more stable than the primary carbocation. If the secondary carbocation is more stable than that of the primary carbocation, its concentration would be more than that primary carbocation, and in this process this intermediate will be in the major concentration and this intermediate will be in the minor concentration. Okay, now here Cl will attack on this carbon. Okay, and here the Cl negative will attack on this carbon. Okay, when Cl will attack on this carbon, it will get a CH3 CH2 CH2 and Cl. This is 1-chloropropane. Sorry, I have taken the bromine here. Sorry dear, I have taken the bromine here. So instead of chlorine, we will take here as a bromine. We'll take a bromine. Okay, we'll take a bromine. Bromine will attack here and bromine will attack here. Okay, bromine will attack here. Okay, now see what will be the product. Well, the product is here the Br, that is one bromo, that's one bromo propane, one bromo propane. And what's the product here? When Br will attack here, it will give us the product as CH3 CH Br and CH3. It is 2 bromo propane. This 2 bromo propane. Okay, this is the reason why the major product is this one. Now, after seeing this mechanism, a Markovnikov gives a rule that's known as Markovnikov's rule. Okay, what does the Markovnikov's rule say? See here. I will write here. We can add HBr or HCl or HI on the unsymmetrical alkenes by the rule known as the Markovnikov's rule. Okay, see here. We have Markovnikov's rule. Markovnikov's rule. What does this Markovnikov's rule states? Okay, it states that the negative part of the reagent that we have taken here, it has two parts. One is the positive part and another is the negative part. It says that the negative part of this reagent will get attached to that double bonded carbon which has a less number of hydrogens. Okay, now see here. That is the negative charged part of reagent gets attached to that double bonded carbon, which has less number of hydrogens. Okay, now see here. In this substrate we have two double bonded carbons, that's carbon 1 and the carbon 2. Okay, in these two carbons, which one have less number of hydrogens? My dear, the carbon number 2 has a less number of hydrogens. That is, this Br negative will attack on this second number carbon. And this rule will give us the major product of this substrate. When we attack this Br here, it will give us 2 bromo propane. That we have already discussed that 2 bromo propane is a major product. Okay, clear? Now we can explain this Markovnikov's rule by a second statement. Okay, now see here. Copy this or take a screenshot of this. Okay, now see here. We'll move on the next. See here, my dear, we have said that Markovnikov's statement. We can write Markovnikov's statement in another way, that hydrogen will get attached to that double bonded carbon which has more number of hydrogen atoms. Okay, now see here. If I will take this one CH3, CH2, CH double bond CH2, and I will treat it with HCl. My dear, what will be the product according to the Markovnik's rule? Okay, Markovnik says that the negative part of this reagent, or we can say the hydrogen of the reagent, this is a hydrogen H plus and this is a Cl minus. Okay, we can say that H positive will get attached to that double bonded carbon which has a more number of hydrogens. These two carbons are double bonded carbons, and this is the carbon number 1, this is the carbon number 1, this is the carbon number 2, carbon number 3, and carbon number 4. This hydrogen will get attached to the carbon first because it has a more number of hydrogens than this carbon. Okay, now we can say that the product will be like this: CH2 CH single bond. There is already 2 hydrogen and 1 hydrogen gets attached here. It will form a CH3. Okay, and this bond will break down. Okay, this bond will go there and the hydrogen will get attached here, and the positive charge will create here. On that positive charge, the Cl will get attached here. Okay, we can see this product by both the statements. The statement first, that negatively charged part of the reagent gets attached to that double bonded carbon which has a less number of hydrogen, that is the negative part, and it gets attached to this carbon because it has a less number of hydrogens. And we can say that second statement, that the hydrogen of this reagent gets attached to that double bonded carbon which has a more number of hydrogen, that this H will go there, and this is the major product according to the Markovnik's rule. Okay, now dear, this product is 2-chlorobutane. This is a 2-chlorobutane. Okay, clear? And we have taken that but1ene. From but1ene, when we treat it with the HCl, and it will give us 2-bromobutane as a major product. Clear? This is the Markovnik's rule. Okay, now see one more important question here. If I will take the alkene, while the intermediate will be secondary carbocation, that secondary carbocation will get first converted into the tertiary carbocation. Okay, if there is a possibility for the secondary carbocation to get converted in the tertiary carbocation, the secondary carbocation will get first converted to the tertiary carbocation, then the negative part will attack. Okay, firstly the carbocation will form. If it will be the secondary carbocation, if there will be the possibility of that secondary carbocation to be converted in the tertiary carbocation, it will get converted in the tertiary carbocation. After that, the negative part will attack. Okay, see the product, see here. I will move here. See, my dear, if I have a substrate like this, CH3 CH3 H CH double bond CH2. Okay, if I will treat it with HCl, what will happen? According to Markovnik's rule, this H plus, it will give H plus and it will give Cl minus. This H plus will attack on this carbon number first. Okay, and we will get this kind of intermediate, CH3 H CH plus and CH3. Okay, because this will attack here and this bond will go along this. Okay, and this H will get attached to here and the positive charge will get created here. This carbocation is a secondary carbocation. Yes sir, this is a secondary carbocation. What is secondary carbocation? This carbon on which the positive charge is created, it is connected to 2 carbon atoms, one on the right side and one on the left side. Then it is the secondary carbocation. Okay, is there any possibility that this secondary carbocation will get converted into tertiary carbocation? If there is a possibility, then this secondary carbocation will get first converted into the tertiary, and after that the negative part will attack here. Okay, see here. Now this hydrogen will go here in the form of H negative, that we can call hydride shift. Okay. Why it's called hydride shift? Because the hydrogen here will move as a H negative. Here this H negative will get shifted to that carbon, okay, and the positive charge will get created here, okay. What will be the intermediate? The intermediate would be like this, CH3. The hydrogen will shift here. It has already one hydrogen, and this hydrogen will get shifted here, and it will get two hydrogens. It will CH2 and CH3, and the positive charge will get generated here. Okay, my dear. Now this secondary carbocation has got converted into a tertiary carbocation. Okay. Now this tertiary carbocation, there occurs a hydride shift. Now on this tertiary carbocation, the Cl negative will attack. Okay. Now Cl negative will attack. The Cl negative will attack here, and it will give us compound like that: CH3, CH3, Cl, CH2 and CH3. Okay, dear. See, this will be the major product, and this product is called a rearrangement product. This is called a rearrangement product. Clear? Okay, now if we see the Markovnikov rule, according to Markovnikov's rule, you can do that H will attack here and positive charge will get created here, and the Cl will attack here. But it doesn't happen. Why? Because this secondary carbocation first gets converted into the tertiary carbocation, and after that the Cl negative will attack here. Okay, and this is a product, and you can write the name of this product, that is 1, 2, 3, 4. This is 2-chloro, 2-methyl butane. Okay, dear. This is the one more question, that's the rearrangement product and the rearrangement process. Okay, now see here, we have once again one more process. Now see here, if we have the unsymmetrical alkene like that, and we add HBr here, but we take here the peroxide. Okay, now in presence of peroxide, the HBr will attack on this alkene. This is unsymmetrical alkene, but here the Markovnikov's rule is not followed. It will proceed by anti-Markovnikov's rule. Okay, that anti-Markovnikov's rule we also call that it is the peroxide effect, or we can say that it is the Karash effect. Okay, now see here, my dear, the product will be like this: CH3, CH2, CH, and here will be CH2, and this bond breaks down. Here is H plus and Br minus. In Markovnikov's rule, we were saying that the hydrogen will attack to that double bonded carbon which has the more number of hydrogens, or we are saying that the negative part of this reagent will attack to that carbon which has a less number of hydrogens. Okay, it was the Markovnikov's rule. But in case of the peroxide, the opposite thing occurs. What will happen? This H will attack on this carbon, okay, and this Br will attack on this carbon. Is it anti-Markovnikov? Yes, sir, it is anti-Markovnikov, because according to Markovnikov, the Br should go to the second carbon, but in this case, Br has got the carbon number 1. Okay, it has attacked on the carbon number 1. It has attacked on the carbon number 1. Okay, this is 1-bromo butane. 1-bromo butane, and this is according to anti-Markovnikov's rule. Anti-Markovnikov's rule. Okay, this is called the anti-Markovnikov's rule, or we can say that it is the peroxide effect. It's the peroxide effect. Okay, or we can say it's a Kirash effect. Okay, sir, it is opposed to the anti-Markovnikov, that's why we call it as the anti-Markovnikov. Yes. Sir, this effect is due to the peroxide, that's why we call it the peroxide effect. Yes, and this effect was first stated by the Kirash, and that's why we call it the Kirash effect. Okay beta, clear? Now this mechanism is due to free radical reaction. Okay, here the mechanism is free radical mechanism. Free radical mechanism. First we said that the addition will take by the electrophilic addition, now according to the Markovnikov, but opposite to that of Markovnikov, in case of peroxide effect, the reaction proceeds through the free radical mechanism. Okay, now I will see the free radical mechanism. Okay, it will take us 2 to 3 minutes. Okay, I will show you how this reaction proceeds. Okay, see here. Okay, see here, we have any peroxide, that is C6H5, C double bond O, C double bond O, C6H5. This is called benzo peroxide. This is called benzo peroxide. Okay, this peroxide will break down with the help of the light. Okay, here occurs a homolytic fission. This oxygen has a same electronegativity that of this oxygen, and it will get as a homolytic fission. Okay, when there occurs a homolytic fission, we get the free radicals C6H5, C double bond O and O dot. This is a free radical. Okay, here we get one part here, that's C6H5, C double bond O dot, and here is also C6H5, C double bond O. Then we get 2 molecules of the benzo peroxide. Okay, this is the free radical. Benzo peroxide will dissociate into 2 free radicals. Okay, now in the second step, this peroxide C6H5 has given us this radical. In the second step, this radical will break down HCl. Okay, this will break HCl. If we have a radical and it will dissociate this molecule as a radical, okay, it will make this compound to break like this. Okay, and this is also a free radical. Here gets H dot and we get here Cl dot. This H dot will combine with this, it will form C6H5, C double bond O and OH. This is a benzoic acid. This is a benzoic acid. Okay, and here in this setup Cl radical has been generated. Okay, Cl dot, that's chlorine radical. That's the chlorine radical. The chlorine radical has generated. It's a chlorine free radical. Chlorine free radical has generated in this step. Okay, now in the third step we have alkene, that is CH3, CH2, CH double bond CH2. Now on this alkene, the free radical chlorine will attack. Okay, now there are 2 possibilities. If this Cl dot will attack here and this bond will break down as a homolytic, there occurs once again a homolytic fission, and this carbon gets 1 electron and this carbon gets 1 electron. Okay, now if Cl will attack on the first carbon, the radical will get generated on the second carbon. And if Cl will attack on the second carbon, and the free radical will get on the first carbon. Okay, now if Cl will attack here on the first carbon, the secondary radical will get generated. If Cl will attack on the second carbon, the first degree free radical will be generated. Okay, what is the preference? Which is the more stable? Sir, we know that the secondary free radical is a more stable than the primary radical, that's a first degree radical. So that we can say that this chlorine radical will attack here, so that it can generate the second degree radical. Okay, now it will form like this: CH3, CH2, CH. Here will be the radical and it will be CH2 and Cl. So secondary radical has been generated here and the chlorine has attacked on the first carbon. Okay, now see, okay, in the first step, this radical, this second degree radical has generated here. This second degree radical CH3, CH2, CH, radical CH2 and Cl. Okay, now this radical will get reacted with HCl once again. It will get reacted with the HCl once again. See here, my dear, see here, it will get reacted with one more molecule of HCl, and we have the radical here. And this radical will break this molecule as a homolytically. Okay, now this will get once again homolytically cleaved. This get H dot and Cl dot, and this H dot will attack here. Okay, it will give us product as CH3, CH2, CH2, CH2 and Cl. Okay, clear? Now see my dear, okay, now I have shown you all this, that in this process, this benzo peroxide will dissociate into radical. This radical will dissociate HCl molecule and it will get attached. This chlorine will get attached on the first carbon and the hydrogen will get on the second, and this addition has taken place. Opposed to the Markovnikov. That's why we call it as an anti-Markovnikov rule. Okay, and this reaction has proceeded by free radical mechanism. Okay, now we have seen both the mechanism, that is, on unsymmetrical alkenes the addition of HBr takes place according to the Markovnikov rule, and on the unsymmetrical alkene the addition of HBr will take according to the anti-Markovnikov rule when we use the peroxide here. Okay, now one more question is here. This rule, that's the anti-Markovnikov rule, is applied only for HBr. It's not applicable for HCl, HI and HF. It's only and only applicable for HBr. So if we do the questions, we will do questions when we see HBr with peroxide, we will proceed by anti-Markovnikov rule, and if we see HBr without the peroxide, we will go through the Markovnikov rule. Okay, clear? Now see here, I will give you the one question so that we will conclude these all the three types HBr addition, okay, on the unsymmetrical alkene with the Markovnikov and anti-Markovnikov and with the rearrangement. All the three we will conclude these three products in a one step. Okay, see here, my dear, see here. I'm taking CH3, CH. Okay, I will show like this so that it will get easy for you people. CH3, H, CH, double bond, CH2. Okay, clear? Now if I add HBr here, okay, if I will add HBr and peroxide here, HBr and peroxide here. Dear, Write the product. Write the product very fast. Very fast. What will the product? HBr with this and HBr peroxide with this. Okay? Okay, dear? Okay. Here it will be CH3, Br, CH2 and CH3 because rearrangement occurs. Okay, because H will attack here, positive charge will get created, H will get shifted here, positive here, and Br will attack here. Okay, clear. Now HBr peroxide, there Br will directly attack here, the radical will get attached here, and H will attack here. Okay, the product will be CH3, H, CH2, Br. Okay, these are the two products. One is with the Markovnikov rule and the rearrangement, and second is the anti-Markovnikov. So there is no rearrangement because radical will get generated. If H will shift here, then there is also radical, and on that radical the H dot will also attack. So here is the no need of the rearrangement, but here will take an rearrangement. Okay, clear? Okay, dear, we have completed this alkyl halides from the alkenes. Okay, we have done all the questions. That's the Markovnikov rule, anti-Markovnikov rule, rearrangement products. Okay, all this. Now in the second lecture we will go with another preparations. Okay, for this lecture. Okay, it's enough. Now we will meet in the next lecture. Till then, goodbye. Thank you.